who will talk about harnessing triplet excitons in organic solid state lasers. So when you're ready, please.
So thank you, Bronson. And I'm Atul Shukla from University of Queensland. And I'd be talking about one of our recent works about harnessing triplet excitons in organic solid state lasers. So this is just a brief outline of my talk for today. I'll start with giving a brief introduction to the field, because many people here won't be familiar with organic lasers in general. Then move on to some of the recent developments in organic lasers, then talk about the research gaps, and finally talk about our results, which talk about solving these research gaps briefly. So why do we need organic semiconductor lasers? And the main motivation basically starts with the fact that these organic semiconductors can give high gains. In most of the situations, these gains are comparable to the inorganic counterparts. They have low processing cost, and they show wide spectral tunability, as shown in this work by Professor Carl Leo's group. They have mechanical flexibility, they are lightweight. And with electrical pumping, it also opens the prospects of on-chip applications of these semiconductor organic lasers. So the reason behind the stimulated emission is basically these organic semiconductors offers an intrinsic four-level system which allows for population inversion. And this is explained by a simplified Jablonski diagram in this image. So we have the absorption step. This is all under optical excitation. We have the absorption step, which is followed by a quick vibronic transition. And after that, there's spontaneous emission. And the spontaneous emission is basically in the linear regime and governed by the Einstein coefficient A. But once we have enough population of these excited states, we can have stimulated emission, which is further governed by the Einstein coefficient B. Now, looking at these equations, we find that if we want to have population inversion at low population density of the excited state, we want our Einstein coefficient to be as high as possible. And in organic semiconductors in general, we have the Einstein coefficient directly related to the stimulated emission cross section, which is further related to the radiative rate of the material. So mostly for stimulated emission, we utilize materials with high radiative rates. So phosphorescence and TADF emitters are basically not possible. It's not possible to get stimulated emission with phosphorescence and TADF materials, while there have been some reports of stimulated emission from TADF materials, but mostly we only use fluorescent emitters. Now, talking about intrinsic gain, but we also have losses in our system. And in order to have net positive gain, we need to have intrinsic gains higher than the losses in the systems. So let's look at how the losses originate in these systems. So under optical pumping, 100% excitons that are generated are basically singlet excitons. And triplet excitons are generated through intersystem crossing. So the main pathway of loss in this system is basically reabsorption losses. There are also singlet triplet annihilation and singlet annihilation losses, but under nanosecond optical pumping, STA doesn't really play a major role. But when we move on to electrical pumping, we are handicapped basically firstly by the singlet generation yield, that is just 25%, and we have 75% triplet excitons, which have a very long lifetime. So not only the population is higher, they can also accumulate over the period of time. So the singlet triplet annihilation losses are extremely high, and there are also additional losses such as singlet polaron annihilation, field induced quenching, and losses due to electrodes. So this makes electrical pumping a major concern and a big challenge for the community itself. And this is what we would try to do, is to manage these triplet excitons so that we can get better performance of these materials. So just looking at the brief history of organic semiconductor lasers. So organic semiconductor lasers by themselves are not really new. They existed over 50 years. And initially they were used as dye lasers, but with development of organic semiconductor, the research in this field started to increase, and there has been a quest for organic laser diodes ever since. And initial work was mostly related to the reducing the size of the pumping source, but reducing the size also puts limitation on the power that we can put in, and even the temporal resolutions of these temporal pulse widths of these sources. So we have to reduce the thresholds for using such sources. And then another major breakthrough was achieving CW lasing in these materials, which was shown by firstly by Professor Stephen Forrest's group, and then by Professor Adachi's group. And much recently, there has been indication of current injection lasing from organic semiconductors, which is really inspirational for people working in this field in general. But even after such comprehensive developments, there are significant research gaps. And one of the major things, when we plot the threshold, AC and laser thresholds for organic semiconductor as a function of wavelength, we clearly see that there's an increase in threshold with longer wavelengths. And that is mainly because of incremental non-radiative losses, as well as aggregate induced quenching for materials emitting, especially in red regime. So now if we take an average of these values here and get a rough estimate of the current density required to achieve these thresholds, we'll find that the current densities are much higher than 1 kiloampere. And this excluding the bimolecular losses that we talked about earlier. So this is not really possible to achieve in conventional materials. And when we include the other loss pathways, we find out that STA plays a major, has a major contribution in quenching the singlet excitons at high current densities. And this was shown by our group in collaboration with Bronson last year. And this can also be seen from the current density thresholds becomes really high at as we increase, as the STA is higher. So in order to get close to electrical pumping, electrically pumped lasers in longer wavelength emitting materials, we firstly need to reduce the thresholds, and also need to reduce them, minimize the losses due to triplet excitons, and also get a positive contribution from these triplet excitons so as to reduce the current densities further. And the last two points here mainly deal with managing the triplet excitons judiciously in order to get good performance. So looking at previously utilized methods that were used for triplet management. So this includes use of triplet quenchers. This was shown by one of my colleagues earlier last year, using COT as the triplet quencher. And previously this was shown by Professor Stephen Forrest's group, again, using ADN as the triplet quencher. So this technique works really good in reducing the losses, but the problem here again comes that it doesn't utilize the triplet excitons. And as we showed earlier, that even if we do not really, even if we reduce the triplet losses, the thresholds are still very high for these materials. So we instead used a TADF assisted fluorescence approach. And previously this scheme has been used commonly in OLED devices. This was used by Professor Adachi's group in 2014, and also referred as the hyperfluorescence. And much recently, this technique has shown really good results for deep blue emitting materials, OLEDs with high stability. So Moving on to our approach, so this is basically the energy level diagram, and we use a host matrix and a TADF assistant dopant, which basically recycles the triplet excitons, converts them into singlet, and then that singlet exciton can be transferred into the laser die by Foster resonance. And we don't want triplet excitons to be transferred to our laser die by Dexter energy transfer, as they would be lost if they move to the conventional laser die. And we basically used a high performance CBP host as the main host material, and CZDBA as our TADF dopant, and DPP as one of our laser die for light amplification. We basically used this combination because it's been reported to give very high RISC, and DPP because it gives a decently high radiative rate. This material has been conventionally used for different applications, OFITs, OPVs, and also singlet fission. But we found that there are very less reports of light amplification from DPP systems in general, even though they have very high, decently high radiative rates. So looking at the properties of the laser die itself, we found that they have very high PLQI, but in neat film, it shows very strong aggregate-induced quenching, so reduction of PLQI because of that. And this makes it essential to use host guest system. And the host matrix that we used basically were just CBP host for comparison, and the TADF host for a main work. So this figure shows the PLQI as a function of DPP doping ratios. And as we see at lower doping ratios, we get higher PLQI from the TADF assisted blend. This is majorly because of better energy transfer, and some contribution also comes from the recycling of triplet excitons. But when we go to higher concentration, we find that it's very much comparable to the normal CBP host. That is because the Dexter energy transfer becomes more prominent at higher doping ratios, which leads to reduction in PLQI. And the evidence of triplet upconversion can be seen here in the system through this delayed fluorescence. And the evidence of increased Dexter from CZDBA to DPP can be seen here in this TCS-PC data. So we can see the reduction in delayed fluorescence, which corresponds with the quenching of triplets of CZDBA itself. So we moved on to the light amplification characteristics, and we just studied the cavity-less lasing, which is also referred as ASC. So in case of TADF assisted blend in 1 weight %, we use 1 weight % to begin with, because it has the highest triplet upconversion amongst all doping ratios. So we got lower ASC thresholds in case of the TADF assisted fluorescence system as compared to even CBP, which is really good. That just signifies that we can get high triplet upconversion as well as low threshold simultaneously in the system. And changing the doping ratio, we found that 1 weight % still gives better performance as compared to other. It's either comparable or it's either lower than other doping ratios. Now, other question that usually comes in, that what happens if we reduce the doping ratio of DPP? So in order to study that, we did ASC measurements for different lower doping ratios. And this figure just shows the input-output curves. So as we see for 1 weight %, we see similar thresholds as compared to 0.758%. But we find that there is a difference in the saturation intensities, which is an indication of increased bimolecular quenching in these systems. And for 0.58%, we do not see any light amplification. It deviates from the slope 1. That is again because of increased bimolecular quenching processes. So in order to really see the effect, why this happens, we did some high resolution energy transfer estimation. And we found out that the 0.58% doping shows higher rise times. As a result of this, longer rise times is poor energy transfer. And due to this, we have the lifetime of the DPP being dominated more by the TADF material. We have lifetime of close to 17 nanoseconds in case of 0.58%, while in 1 weight%, we had lifetime of 9 nanoseconds, which is close to the intrinsic lifetime of DPP. So this also, again, helps us to understand why there is increased biomolecular quenching in case of lower doping ratios. So these results were really good, but we also wanted to study if triplet excitons are leading to losses in this system. So we did some transient absorption spectroscopy to get the estimation of triplet absorption band, because that shows how much the STA would impact our devices under electrical pumping. So this shows the transient absorption signals at different time delays. And we can see the triplet absorption band here. We further converted into the cross-section, estimated the cross-section, and we could see that there's appreciable overlap between triplet absorption of DPP. That is, when we talk about DPP, it's basically a system where it's only CBP and DPP, and triplet excitons are confined on DPP itself. So we see an appreciable overlap, which shows that there would be significant contribution from STA in this system. When we moved to CZDBA, we found that we cannot really detect any triplet absorption band in our measurements. All of these signals that we had in global fitting, it showed only by exponential fit, which technically corresponded with lifetimes of emission lifetimes, that is prompt and delayed lifetimes of CZDBA. So the reason behind this can be because the triplet absorption band for CZDBA lies outside the probe wavelength of our instrument, which is good, because in that case, we do not really have much triplet losses in systems where triplets are confined on CZDBA. So now moving on to devices, we used a very simple device structure, solution process device structure. And as you could see in the comparison in this figure, the devices that has 10% doping of CZDBA show significant improvement as compared to just CBP DPP devices. Not only the EQE, peak EQE is higher, but the roll-off is also much lower in devices with CZDBA. So this is really good. So next we wanted to see how far we can go into these devices and how much current we can put in, because lasing requires very high current densities in order to get stimulated emission. So we firstly used this pulse measurement setup. We had variable pulse generators to inject high current densities, and we detected the signals using the PMT. And then we estimated the current density that would be required in order to really achieve that singlet population to get to the AC threshold. And we got a threshold current density of close to 300 to 400 amps per centimeter square in case of devices that had CZDBA, while very high current density of close to 1.3 to 2.7 kiloamps in case of devices without CZDBA. And this estimation basically doesn't really take into account the losses due to electrodes or losses due to biomolecular processes. So it's a very rough estimate. So this number basically is really low. And if you look at the measurements that we have done earlier, we have been able to inject such high current densities regularly in such systems using very short pulses of just 100 nanoseconds. So firstly, we performed the pulse measurements with these materials under 100 nanosecond pulse for just DPP CBP system. And as we can see here in the luminance as a function of time, the transient luminance for these OLEDs, we can see strong quenching of emission as we increase the voltage in the devices. And this is more clearly shown in the normalized yield curves. and further in the EQE roll loss. So, which is evident because we saw very high overlap between triplet absorption and emission wavelengths of DPP. But when we moved on to CZDBA CBP blend, we found that as we increase the pulse width, the EL intensity tends to increase. So we can no longer use 100 nanosecond pulse, which is logical because the triplets take time to get back to singlet excited state through RISC, which has its own limit. And the evidence of increased triplet up conversion with increasing pulse width can be seen in this decay curves. So this, because of longer pulse width, we can no longer really inject high current densities. So we tried with 2 pulse width, basically 5 microseconds and 1 microseconds. So in initial lower voltages, we found that the 5 microsecond pulse has slightly better performance, but this tends to become similar to the 1 microsecond pulse width results. And the reason for this being the saturation of early saturation of the transient ELs, which is mainly because of the quenching of triplet excitons itself due to PTA, TPA, and in these systems, there's an additional loss mechanism, that is Dexter energy transfer to DPP. So all of these losses are expected to increase. So even with 1 microsecond, we were able to inject close to 60 amps of current, but that's surely not enough in order to get current injection. And also we see very strong roll-off in these materials. That is again because the quenching of triplet excitons itself. So if we are able to increase RISC, we would be able to solve a lot of these issues that are coming just by the quenching of triplet excitons. So coming on to conclusions, we were able to still demonstrate low thresholds and high EQE with the TADF assisted system. And even though we were able to reduce STA, main concern here is the quenching of triplets itself. So the higher RISC would be able to allow us to go to nanosecond pumping regime again, which further allows us to go for higher current densities and also reduce the biomolecular quenching processes. And lastly, to reduce the Dexter energy losses to the end emitter, we would technically want our laser diode to be sterically protected so that this Dexter energy transfer is reduced. And I would like to thank my supervisors and all the group members and Dr. Sarah McGregor, especially for making the DPP laser die for me. Thank you.
Thank you very much. Another very interesting presentation. So once again, we'll open up for questions. If anyone would like to ask, you just need to unmute your microphone if you have questions. If not, maybe I could start. So could you speculate about what could be achieved with the steric hindrance you mentioned to suppress that Dexter energy transfer? Do you have any thoughts on what's possible there, and you know what would be sort of you know, conceivably you know, what could be achieved with that strategy?
So yeah, basically the Dexter radius in organic molecules, it's basically few nanometers, while Fred radius, we can use systems which have like 8 to 9 nanometers of Fred radius. So if we have statically protected groups and we can just reduce that distance between the main core, like a dendrimer structure, we can probably get rid of, or at least reduce Dexter energy to save our triplet excitons in the TADF material itself. And this is shown by Professor Uli Lemma's group earlier last year, I think, through simulations as well as experimental results.
Yeah, excellent. Thank you. Yeah, seems like a really interesting strategy to pursue.
Yeah.
Can I ask a question? So your EQEs were actually sort of relatively low for materials that have the hyperfluorescence in them. How does that, and that could be in part due to the relatively simple device architectures that you've had. How do you think having a sort of a more complex, if you like, device architecture to really balance your holes and your electrons and maximize the EQE would affect the ability to get your electrically pumped lasing?
That's true. I think we didn't really try to get a very good device because our aim basically was to study how the system behaves, but that's surely possible. And we did try later on in few of the studies to get better device structure, but we found out that the roll-off is significantly similar. So at the end, at higher current densities, we get very similar, because the current densities we are talking about is beyond the operational OLED device architecture, device limits.
Sure.
So the charge balance, no matter what we do, is difficult to obtain at better device structures. So even if we get like 2% EQE, we technically want that to go up till 100 amps. So peak EQ is basically not really the question that we deal with in our work.
So just on that, I mean, the current density, how long do these devices actually last? I mean, you're really hitting them, right? And if you wanted to get them into markets, your laser has to last a reasonable length of time.
That's true, yeah.
So how long does each pixel last under these sort of high driving conditions, current driving conditions?
That's true, and that was basically the main problem with the first OLD that was reported. They would last for 2 minutes, 3 minutes, and that makes difficult to characterize it. But it again depends on material to material. In some cases, like if we manage the triplet excitons, they can also help in increasing the device stability with triplet quenchers. But yeah, normally if we go for like anything above 100 amps, they don't last more than 5 minutes in general for 50% degradation limit.
Okay, thank you.
Were there any other questions from anyone? If not, then thank you very much, Atul. Interesting presentation. Yeah, so as Paul mentioned, we're having a break now, so there will be no seminar on the first Wednesday of January. I guess everybody will be on holidays at that point, and we'll be in touch with our plans for the new year. So have a good holidays, everyone, and yeah, we'll see you in the new year.